So there's a homework due tonight. It's homework 6. And I'm doing the rest of the notes for chapter 16 today. And the first thing we'll do is help with the problems that are on homework 6 that involve counting plus probability. I'm going to post exam 2 tomorrow. It's going to be due next week on Thursday, and Tuesday and Thursday in class we'll review for the test. I'll just help you with similar but different questions. Okay. So for the rest of chapter 16, we're just putting our notes from how to find probabilities together with how to use counting techniques to solve a few more problems. And then we'll just go back through everything we've learned next week. Okay. So there's one more thing to go over. It's when you have independent events. So if one event doesn't affect another event, like when you flip a coin and then you flip another coin, that first coin flip doesn't affect the other one at all. Or if I grab a candy out of a jar and then I grab a toy out of a box, each of those selections didn't affect each other. They're independent. And I think it takes a few examples and practice problems to kind of recognize when events are independent or dependent. And we'll do our best today. But if your events are independent, then you can use this rule. It's a multiplication rule only for independent events. So we'll call the events A and B. Okay, so once you've kind of checked that the of one event doesn't affect the probability of the other event, they're independent, and you want to know the probability of both events happening, you can use the probability of the first event and multiply it with the probability of the second event. So we could use probability of A and B, or intersect B, is the probability of A times probability. I think we should do a quick, easy one. So one we've looked at before is flipping a coin 2 times. And I mentioned earlier, once you do the first flip, and then you do a second flip, they have nothing to do with each other. One flip has no impact on the other flip. Okay, we're going to find the probability of getting all heads, or 2 heads in a row. Okay, so first we're going to talk about it the way we used to. We'd find a sample space, find the number of ways that event can occur, divide by the total. But after that, we're going to talk about using this rule instead. So back to before, when we looked at this kind of sample space, one way to look at it is with a tree diagram. That's one flip, and then you flip again. Okay, so it's all the way to the end of the top branch is where you have all heads. And just pointing out that all the way at the bottom branch, when you get down to the end, that's the path that leads, or that's the outcome that has all tails. So there's only one way to have all heads and one way to have all tails. Let's list out each occurrence. There's heads, 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 tails. Tails, heads. All right. I'm just going to mention right away that in a lot of these examples, there should be a lot of extra curly brackets. I'm going to drop the curly brackets just to help explain the problem. But if we wanted to really stick to notation, each of these events should be a set, technically. This is what I mean. So what we asked is probability of all heads, which should be written like this: the set or the event of heads followed by heads. But a lot of statisticians would just put probability of heads. Okay, and this is the old way we used to do it. You find this, the number of ways this happens, which is just one once, and then divide by the total number of occurrences, which is all 1, 2, 3, 4. Or you know that you have one flip is independent of the other flip. So we're going to do this with the multiplication rule for independent events. So they are independent. Probability of heads followed by heads, or heads and heads, is the probability of heads, and then multiply with the probability of heads. And that comes from being independent events. Heads and heads is probability of the first multiplied with the probability of the second. Probability of getting heads, since it's a fair coin, is heads or tails, it's 1/2 of the time. Or two choices, heads and tails. There's only one choice here. Heads. Same probability for heads on just one coin flip, where you're thinking it's heads or tails, and this happens half of the time. Same result. Okay, let's make this tricky. We are going to flip a fair coin six times. Oh, actually, there's going to be a two-part problem. Okay, flip a coin, we flip it 6 times in a row, it's a fair coin. And probability of part A getting all heads, or heads 6 times. Okay. Again, technically each of my events should be written as a set, but we're going to drop the curly brackets just to get kind of more to the point of the problem. And in this problem, I'm going to start with my 6 flips. And if it's all heads in a row, it means it's H in every spot. And we want to find the probability of getting H 6 times. Every flip is independent of the other. So this comes from the rule, since flips are independent, it's probability of H and H and H and H and H equal to probability of H multiplied with itself 6 times. Six. Okay, it's a fair coin. So heads is the same as tails. It occurs half the time. Probability of getting heads on 1 coin flip is 1. And you're multiplying it with itself 6 times. So I'm just going to write that you have 1/2 to the 6th, or 1/2 to the 6th, either. I got 1/64. Part B finds the probability of getting either all heads or all tails. Okay, to save a bit of writing, we're going to call event A all heads. And B is where you get all tails. And we're asked to get the probability of A or B. So need probability of A union B. all heads or all tails and get the probability of that. Okay, so what we're using now is the general addition rule. Wait, yes, the general addition rule. So it's the probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. Okay, probability of getting all heads was part A. It's 1/64. All right, plus. This is the probability of getting all tails. So it's very similar to getting all heads, but we're going to talk through it for a second. This is like extra scratch work aside from your scratch work. Probability of B means probability of all tails, which is 6 tails in a row. And this is for independent events. Each flip is independent of the next. So you can multiply all of these together 6 times. Okay, but it's a fair coin. So the chance of getting heads is the exact same as the chance of getting tails. It happens half the time. You're multiplying 1/2 with itself 6 times. So it's another 1/2 to the 6th. Or 1/64. And this last one is the probability of getting all heads and all tails, which is not possible. It can't be all heads and all tails. It's the probability of the empty set, which is 0. Okay, so this is 2/64. Which is 2/2 times 32. 2/2 is 1. And this is 1/32. Okay, we're going to do one with an unfair coin. And then we're either going to switch to talking about dice or locks. So let's see. This unfair coin has a probability of landing 0.6 on heads. All right, we're going to toss this coin 4 times. Okay. What is the probability of all tails? Okay. We know probability of heads. Scratch. This part. Probability of getting heads is 0.6. Okay. And the total probability is 1. So it's heads or tails. Chance of getting tails is 1 minus 0.6. All right, and then we flip a coin 4 times in a row. So I guess this is just something I learned from when I took stats, is to make kind of a little visual placeholder. You don't need to though. There's my 4 flips. I want all tails 4 times. And we want the probability of getting this. Tails and tails and tails and tails. Since each flip is independent of the next, we're going to multiply probability of tails with itself 4 times. Okay, this time, since it's an unfair coin, we need that probability for tails of 0.4. I'll multiply that with itself. 0.0256. Next, we're going to roll a die 4 times. and find the probability of getting 2s every roll. So all 2s. So all of the same number, and that number is 2. So every time you roll, you got 2. And there are 4 rolls. So I do this 4 spaces. Each time I can choose between 1 and 6, each side of the die. But in this example, we're saying that the roll is a 2. And then you also got another 2. And 2. And I'm getting the probability of this. And if I left out the intersection sign, but it's 2 and 2 and 2 and 2. Since each roll is independent of the next roll, we're going to take the probability of getting a 2, multiply with the probability of getting a 2 4 times. So for one roll, 2 occurs once out of all 6 possibilities. So it's 1/6 for each of these. So all of those probabilities, it's that one outcome, the number 2, out of the 6 outcomes, 1 through 6. And again and again and again. This is 1/6 to the 4th. Or 0.0046. Okay. So the problems we've done should help you with one of your homework questions. This one is also similar to a homework question. You have a lock and it has 4 rotating discs. Okay, each disc has letters A, B, C, D, E, and F. And then split this into two parts. The first part is A, how many lock codes are possible? Oh, also, it matters if you can repeat a letter or not. We can repeat letters. Actually, never mind. Let's do it where we cannot. So you can, a letter cannot be repeated. Okay. So you've got 4 discs. 1, 2, 3, 4. Each has the traces A, B, C, D, E, F. How many codes are possible if a letter cannot be repeated? So for the first spot, I have 1, 2, 3, 4, 5, 6 choices, 6 letters to pick from. And then I pick one. Let's say I pick C. So if C is the first letter, and I can't repeat it, so in the next spot, I've got 1, 2, 3, 4, 5 choices. I've already used one of the letters and I can't use it again. Similar idea, from these 5, I pick a letter, can't use it in the next position, so what's left to choose from are 4 letters. And then at the end, I can pick from 3 letters, and that way there's no repeated letters. Okay, that would be 360. There's another way to think about this. Or you could use a permutation, because the code, the order in which you put the letters does matter, so order matters. And it's without replacement. So once we pick a letter, we don't put it back. We use that letter, and then we pick another letter, and then we pick another letter. And again, we're putting them in a certain order. So you can, if you want to, use permutations. It would be, out of all the possible letters, which is 1, 2, 3, 4, 5, 6 of them, we want to choose 4 to create, or we want to permute 4 to create the code, because the order matters. Six would be 6 factorial. 6 minus 4 factorial, which is 6 factorial, 2 factorial. 6 times 5 times 4 times 3 times 2 times 1. over 2 times 1. One over 1 is 1, 2 over 2 is 1. So this is 6 times 5 times 4 times 3 over 1, or 6 times 5 times 4 times 3. Just results. All right, part B. What is the probability of guessing the correct code on the first try? Okay. So it's a little wordy, so we're going to mostly talk through it, but you want to do it by using the definition, probability of getting the correct code on your first attempt is the number of ways to do that, and then divided by the total number of possible codes. So we want number of ways, number of correct codes divided by the total number of possible codes. All right, for this numerator, there's only one code that will unlock the lock. So it's just 1 divided by the total of 360. That 1 is the one correct code, and the 360 is the total number of codes that you can make, all possible codes that are can be created. All right. So I did write this as a decimal on a test. You could leave it as a fraction or a decimal, or you can change it to percentage if you want to. This would be about 0.003. This number, if you want to change it to decimal, go here, and it would be 0.3%. It's a very small chance. Okay. A computer has a 5-digit password. The digits are 0 through 9, and digits can be repeated. What is the probability of guessing the correct password on the first attempt? And just mentioning again, the digits can go from 0 over to 9. Okay, so it's a 5-digit password. Digits can be repeated. And do you want to know how likely it is to get the right password on the first attempt? So it's similar to the previous problem where the probability is going to be the number of ways the event can occur divided by the total number of outcomes. And there's only one correct code. So what we need to find is the total number of possible passwords. And then we can piece this together. Okay, so let's see. Let's make a space for every digit, 5 spaces. Each spot, you have the choices 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, which means you've got 10 choices. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 possibilities for your first digit. And then in the next spot, you can repeat any of the digits. So it's another 10 choices. All of the same possibilities can go here. And then another 10 choices because you can repeat digits. And it keeps going like that for all of the spots. Every place has 10 digits to choose from. Okay, multiply all of that together to get the number of different passwords that are possible. Okay, so this is part of finding the probability. The probability is the number of correct passwords divided by all possible passwords. Okay, there's only one accurate password, so it's 1 in the numerator And we're putting all possible passwords in the denominator, which we found out there's, I think, 100,000 of them. So 1 over 100,000. So 0.00001. 4 zeros and a 1. I'm going to keep doing examples till we run out of time. So next one is going to be to have 20 fish in a pond. All of the fish are blue, 8 of them are red. Five fish are randomly selected. What is the probability that they are all blue? For this one, we're going to use combinations. We're choosing 5 fish out of 20 fish. And in the end, it doesn't matter what order you take the fish in. Just scoop them up. It doesn't matter what the order they are in. Ugh. Order doesn't matter. Okay, so probability that you have 5 fish that are blue. I'm going to put all blue. And then we're using the definition. So number of ways to have that event occur. the number of ways to choose 5 blue fish. Out of the total number of ways to choose any 5 fish. I'm going to put this up on the side so it's easier to read. Okay, so number of ways that event can occur. Number of ways to choose fish. And out of the total number of ways to select just 5 fish. Okay. Go back to the problem. Reading through it again. 20 fish in this pond. 12 of the fish are blue. So out of the 12 blue fish, I'm wanting 5 of them. So 5 out of 12, we're choosing 5. Out of the 12 blue fish, choose random 5 of them. Okay, that's the number of ways to choose my 5 blue fish. Number of ways to choose any 5 fish is to go to the total, all 20 fish. Choose any 5. Just choose 5. So I've got 12, choose 5. Divided by 20, choose 5. Which you can work out on scratch paper. You could put into Desmos scientific calculator or Wolfram Alpha. Or ask me for help in office hour. And I got 792 over 15,504. Which is about 0.051. Okay, I'm going to try to do one more and then we'll call it good. So this time we're looking at, instead of a pond with either red fish or blue fish, we're going to look at a toy box. It has 3 kinds of toys. There's stuffed animals that are bunnies or dogs or bears. A child randomly selects 5 toys from a bin. Containing I'm just gonna put 3 bunnies, 5 dogs, and 6 bears. Find the probability that only bears are chosen. You want the probability, P for probability, of all bears or only bears. And we're picking 5 toys from the bin, so we want 5 bears. So we're going to find the number of ways to choose 5 bears and divide by the number of ways to just pick 5 toys. Number of ways that event can occur. Out of the total possibilities, total number of ways. To choose 5 toys. Okay, in the numerator, to choose 5 bears when there are 6 possible bears is going to be out of 6, choose 5. Out of the 6 bears, we want to pick 5 of them. Okay, in the denominator, we're going to all of the toys, which there are, let's see, 3, 9, 14 toys total. Out of 14, we're picking 5. Or we're choosing 5. 14. Choose 5. Okay. 6 choose 5 is 6. And 14 choose 5 is 200 is 2002. 2,002. And this reduced to 3 over 1001. Okay, and I mean, I have a few more examples, but I'll save them for review week. And I think that's as far as we're going to get through chapter 16. So today what we did, just to wrap up what our goals were, was we took the counting techniques of the multiplication rule, permutations, and combinations, used those counting techniques to find probabilities. The first few questions were to help you with your homework. These other few questions were to give you a feel for like how to use combinations and how to find the probabilities. We'll keep practicing next week. And yeah, I'll start working on your test tonight. I'll have it up by tomorrow. So that's the end of chapter 16. After the test, we're doing graph theory, which is a whole totally different topic. We're like moving into a new world when we go into that chapter. Alrighty, have a good weekend. Let me know over the weekend if you need help on your test.
Oh, I have a question.
Oh yeah.
Is it possible for me to